Okay, here we go. Factoring special cases. Now, these are called special cases because um, the binomials that got multiplied together to get these answers all have something in common. They are either exactly identical to one another or they're identical except for the operators. Let's take a look and see why that is and what happens when they look exactly alike. So if I have x plus 2 times x plus 2, and I use FOIL to multiply that out, x squared plus 2x plus 2x plus 4, and then combine the 2 here in the middle, I get x squared plus 4x plus 4. And you'll notice that the beginning term, x squared, is a perfect square. That means it comes from the same thing being multiplied to itself, x times x. And the last term is also a perfect square. The square root of 4 is 2, so this came from 2 times 2. They both will have the same operator, they both will be plus. So when they're identical to each other and it's plus, this is the way that it will look. If they are identical to each other and there's a minus, let me throw another number in here. We'll still use 2. So you see they both have exactly the same numbers and the same operators. So here we go. 9x squared minus 6x minus 6x plus 4. Combine the 2 in the middle. 9x squared minus 12x plus 4. So again, we ended up with the first term is a perfect square. 3x times 3x. 3 times 3 is 9. X times x is x squared. Perfect square. And the last term also is a perfect square. 2 times 2. All right, but what if then we have the same numbers but different operators? 5 and 2, 5 and 2, but minus and plus, or plus and minus. Let's see what happens then. Okay, so 25x squared plus 10x minus 10x minus 4. Now put the 2 in the middle together. 10, take away 10 means 0. These 2 in the middle go completely away, and the final answer is 25x squared minus 4. You have to bring that minus sign with the 4. Well, this is special, isn't it? Now this is the answer to this and not that. So as you're going along, if you have an expression that just has 2 terms in it, then chances are it came from something that looks like this, where the 2 binomial factors were exactly the same numbers, but one was a plus and one was a minus. That's what makes the middle go away. So let's try some of these. Okay, I know, okay, I'm seeing the same thing here. Just 2 terms in this whole quadratic, just like right here. So I'm thinking it came from something that looks like this. And in fact it did, because 16 comes from 4 times 4, and 9 comes from 3 times 3. So this factored into binomials is 4n plus 3 times 4n minus 3. And if we multiply that back out, if we FOIL it, this is what we will end up with. All right, number 3. Here we go again. Perfect square, perfect square. This time I'm left with the term in the middle. Let's see how that's going to work out. I have a minus sign here and a plus sign there. The operators are the same. They're both minus. 16 comes from 4 times 4. 25 comes from 5 times 5. So it is 4b minus 5 times 4b minus 5. See, it looks just like this one did. Minus and minus, and look at what we ended up with. A plus sign here and a minus sign there. Plus and minus, minus and minus. Now, this is a correct way to write the answer, but it's more correctly to write it this way if all the numbers are exactly the same and the operators are the same. This would be the preferred way to write the answer. However, this is not wrong. Okay, so this really does come down to being able to read the signs and know what your squares are. Number 5. Okay, 9 comes from 3 times 3. 1 comes from 1 times 1. There's only 2 terms here. They're both perfect squares. So it's going to end up being like this right here. One's a minus, one's a plus. So 3x plus 1 times 3x minus 1. Now, even though they have the same numbers, they have different operators. So that's why we can't write it like this. In number 3, they both had the same operator. They were both minuses, so we could write it like this. We can't do that with this one. This is the final answer for this one. Okay, number 7. Ooh, n to the 4th. Man, we're doing so good. Then they had to go throw something like that in there. I can't do it. Yes, you can. N to the 4th comes from n squared times n squared. Remember the properties of exponents? If you're multiplying them, you add the exponents together. N squared times n squared, n to the 4th. 100 is 10 times 10. There's only 2 terms. There's a minus sign between them. So 1 is plus, 1 is minus. N squared plus 10 times n squared minus 10. Bada boom, bada bing, it's done. Now let's look on the back. Yes. Woo. Well, on the back, they just get a little longer, maybe a little bit more complicated, but really there's nothing that you can't do. I have to use a little ingenuity here. I have to think a little bit. What we need is for this to be a perfect square. And there is not 2 whole numbers that you can multiply together to get 98. And really, not 2 whole numbers of the same that you could multiply together to get 200. So these are not perfect squares. What would we have to do to make them perfect squares? Well, this is a clue right here. If this were 100, I know that I could do 10 times 10. So if I factor 2 out of this one, it ends up being 100. If I factor 2 out of this one, oh, I get 49. So we're going to start by factoring a 2 out. 49 n squared minus 100. Ah, here we go. Okay, I'm going to forget about the 2 for just a minute. Let's see, there's be a plus and there'll be a minus. 49 comes from 7 times 7, so 7n, 7n. 100 comes from 10 times 10, so 10 and 10. All the factoring is done. We just need to put our 2 there. That is done. Finished, completed. This is the way that you need to think. In fact, if you'll look down the page here, here's what you actually factored right here. And look down here. Oh, look at number 17. Now it doesn't matter if the variable is with the first term or the second term. It doesn't matter. If this had been 200 minus 98 n squared, we would have started out the same way by factoring a 2 out. 100 minus 49 n squared. Now factor this. The 100 comes from 10 times 10. One's a plus, one's a minus. 49 comes from 7 and 7, and n squared comes from n and n. And then put the 2 with it, and we get the same answer. So it doesn't matter. This one doesn't matter. If you want, just flip it all the way around and do 3b squared plus 6b plus 3. This one you'll have to factor a 3 out of, and then you'll be able to factor it as a special case quadratic. So factor out a 3. 10 times 10, 9 times 9. Oh, 7 times 7, 4 times 4. Factor a 10 out to begin with. Ooh, 1 times 1, and I'll let you figure that out. Does 343, is it divisible by 7? Hope so. Ah! What if this were 104? This one, you'll have to factor an m squared out of, just like the 2 here, and then factor the quadratic that remains. I hope this has been a help to you. Don't forget, give me a call if you need to. My number is on the paper I sent home with you. It was on the last video. And one thing that I would like for you to do is if you're using one of the older yellow calculators, be sure and turn it off when you're done using it. I replaced all the batteries in them before I sent them home, but those batteries won't last very long in those calculators, so you need to turn them off when you're done using them for the day so that those batteries will last for a while. I have no way to get batteries to you if the batteries run down. Anyway, send me a message, something, if you get stuck.